Okay, so the topic of the talk is generic programming with Concepts Lite. This is the same talk that I submitted to ACCU, the Association of C++ Users. At least the abstract was the same, and so the title of the talk is the same. But then I felt kind of bad, and I completely rewrote it. So this is definitely a different talk. Plus, it's an extra hour. Well, actually, I guess an extra half hour. Yeah. So this talk is not specifically about a survey of language features for concepts. I mean, that's certainly in there, but it's not the only thing that I actually want to talk about. Really, what I kind of wanted to do when I was thinking about how to present this, and the fact that I had no idea who the audience was going to be, was to present something that kind of motivated why concepts are important, rather than, hey, look, here's a fancy new language feature. You can do X, Y, and Z. I've done that, and it doesn't seem to click very well or connect very well. So I'm going to actually talk about sort of the motivating problems. At least this hour is going to be mostly about motivating problems. The next hour, that sounds terrifying to say, the next hour of the talk will focus on more about concept stuff, actually. So, for most of this talk actually focuses on improving compiler diagnostics, or at least it seems that way, because that's really the most obvious win that we get out of concepts. We don't get gigabytes of error messages anymore. At least hopefully we don't. One of the other features that actually falls out of this is sort of, better support for directly expressing your intent. We don't have to rely on idioms anymore, or some weird cleverness that shows up in our programs. And then something that would sort of taken me by surprise, but I kind of knew that we were going to build this feature in, which is the overloading partial specialization support. But I didn't really know, we haven't really sat down and figured out kind of how that fits in with the rest of C++. And it turns out that when you sit down and think about it and you work through these ideas, you actually get a very good platform for actually defining sort of an open extension model for templates and for functions and classes and things like that. All right, so before I really start, I'm going to go through some contributions and some other information. Concepts, this version of Concepts is the result of a collaboration from these handsome dudes. So that's me on the top left, and then I'm sure you guys recognize Bjarne here. If you don't know Gabby, this is Gabriel Dos Reis. He works at Microsoft now. He's actually one of the guys that kind of pushed me into actually working out the overloading stuff, which turned out to be a pretty good idea. The current state of this is that it's on its way to being an ISO technical specification. We have a working draft. Last published version is N4040. You can probably find a more recent version with the word missing next to it, because I didn't submit an updated version after last conference. There will be a new and updated version of this paper for the November meeting. Please do not grab this paper and assume that it's a very good introduction to concepts. It's not. This is technical wording for the C++ standard. It reads badly. It is almost incomprehensible. And it will not teach you anything about programming or concepts or programming with concepts. That said, hopefully we'll have a PDTS out in November, depending on how much time I can actually commit to rewriting everything that I did previously. If you guys do want good overviews of this stuff, there are a couple of papers I can recommend. The first is going to be N3351, a concept design for the STL. This is based on a meeting back in Palo Alto between, let's see, it's me and Bjarne and Alex Stepanoff and Paul McJones and a bunch of guys from Indiana, Mershon Zalewski, Larice Buffo, Sean Parent was there. Basically, we sat down and we kind of worked out all the concepts that were going to be in the STL and how we wanted to specify them. Sort of a rough sketch of what the language feature should actually be. There have been a couple of papers on the actual language feature itself, roughly titled Concepts Lite, sometimes with a colon after it, like constraining templates with predicates. The most recent overview of that is N3701, called Concepts Lite. So if you guys have time to dedicate to reading 180 pages of introduction material, it's actually worthwhile. Please do not, as I have seen, go straight to the specification and then go onto the proposals list and start making suggestions about concept design. They will not be appreciated. There is an implementation based on GCC 4.10. Previously, the slide said 4.9, so we're following trunk. You guys can get it from here if you have your laptop out and you have enough bandwidth to actually go grab GCC and build it from source during the talk. There will be time to do so. I strongly recommend disabling the bootstrap, otherwise you will not be able to finish. Feature completeness, basically we implement everything that is actually in this talk with 2 notable exceptions, both related to some new features that kind of crept into concepts after the last meeting related to placeholder types. But it's actually fairly stable, minus all the bugs you'll find. But we actually have users, and apparently we're shipping a high-frequency trading platform. Somebody was insane and decided to write against it. And we have a bunch of academic projects that are actually using this. Implementation support. So Jason Merrill is the guy from GCC who's actually been reviewing all the patches, and he'll be responsible essentially for the thumbs up or yes or no for when this gets moved into GCC's trunk, which I think will happen this fall. I hope to talk with him in November, because I think we're actually ready to do that. Braden Oberzud is a student at the University of Akron. He's 21 and apparently quite good at adapting himself to working with GCC. He actually implemented a bunch of stuff for Concepts this summer. And if you guys, does anybody here use GCC? Oh, lovely. If you guys end up using the new variable template features in GCC, he did the first patch of that, and variable concepts and some other stuff. So he's actually a pretty good student. And then, of course, I have to give a little nod to Ville Voutilainen, the soft-spoken Ville Voutilainen, for some, if you guys know him, that's clearly a joke. He actually threw a couple of patches against concepts, which have been helpful for diagnostics. So finally, I have to tell you, there is no library support for concepts because we just decided to punt on that because it turns out that actually building a concept-enabled library is a ton of work, and we wanted to focus on the way that you say things rather than what's actually being said. Now, that actually being said, there is a library out there called, oh, that's not the right URL, called Origin. You can find it from that URL. It's not quite right, just /origin will get you there. And that actually has a bunch of concepts from the in3351 documents, mostly aligned with that. And there's some slight differences, but you'd be able to find your way around. And there's some initial experimental support for ranges. I think Eric Niebler is talking about this week. Is that true? Does anybody know?
I don't think he's here.
Boo. I was going to pick on him if he was. I was actually going to ask him to correct some of my terminology later in the talk. So that's unfortunate. But yeah, so this is some basic range support stuff for concepts based on his work, actually. All right, so the basic overview of the talk works like this. The first hour is really just going to be motivation, and then sort of concepts lightest. Like, I'm going to eventually end up with the initial version of concepts that was never actually published because we were told to fix it and improve it, and that's a good stopping point for the first hour. Then we'll actually talk about what's in Concepts Lite for the second hour. All right. And now I'm going to do something very strange. I'm going to talk about concepts and generic programming in the context of a completely different language. Oh, and my favorite reference from Wikipedia. So generic programming is a style of programming in which algorithms are specified in terms of to be specified later types that are then instantiated when needed for specific types provided as arguments. This is actually a fairly good description of generic programming. Well, it's sort of actually a good description of generic programming from the perspective of what a compiler does, and maybe not how you actually go about doing this stuff. So, guess what language I'm going to start with? No, come on, Haskell? I'm functional programming language illiterate, I'm sorry. No, Python. Curiously enough, I'm going to start with Python. So here's a simple algorithm in Python. Basically, it's the all algorithm. I know it's a built-in, but I've redefined it anyways. It turns out this is totally legal, which is odd to me. So basically, you loop over all the elements in a sequence. You evaluate some predicate. You return false if any of those fail. You return true if all of them succeed. It's a very basic algorithm, right? So the question is this generic? Does this fall into our category of generic programming? And I'm going to answer that in a second. Apparently, my slides are out of order. That's OK. So we can use it. So we can test with, I know that there's an extra function on this slide, by the way. It's not a big deal. It's there for a reason. I know I could write this much more simply. So if we call test with a list of 2 and is even or even, it prints true. Oh my God, I left these. Pretend that says is even and is even. Wow. So we can do this with a tuple. We can do it with a list. We can do it with a string. Turns out to work fine in Python. And then we try to call with a list, and we pass in true because apparently we've misread the documentation, and then bad things kind of happen. So here's what happens with Python. This is a dynamically typed language. So basically, we take so in a dynamically typed language, the type goes along with the object, right? There's nothing static about it. There's this little field that goes along with the type and says, this is what I am, or with the object, this is what I am, and this is how you can use me. So whenever you call this function, that object goes into these algorithms, and the compiler sort of, or the programming language sort of has rules that figure how you look this stuff up. And sometimes you find the right function, and sometimes you don't. And if you don't, you get an exception. If you do, then everything is good. And this is generally called duck typing. So the idea is basically that we can actually look at this as instantiating a generic algorithm based on the dynamic type of an object. And it turns out to work pretty well for a definition of generic programming. More importantly, it gives me a nice basis for actually comparing two different styles of programming that turns out to have a lot of similarities. Right? And this is what actually happens when you run this, that little exception there at the back. What you get is a stack trace. Because what's happened is I've called this function, which calls test, which calls all, which was on the previous slide. And when you look at the stack trace, you can actually see every call in that stack. And I know you're thinking, okay, so who cares? This is pretty boring. I do this all the time. I get these exceptions a lot because I write in JavaScript or Ruby or Python. This is par for the course, right? So it turns out that these type errors are actually kind of nasty. So whenever you use an object or an expression in a way that's not actually supported by the type, the error has to be diagnosed at the point of use. And this always entails some kind of oops, sorry, I'm getting ahead of myself. This always entails some kind of a stack, right? In Python, you get the stack trace. In C++, we get something quite a bit different. So let's move to C++ now. So we want to do two things. We want to be able to achieve the same level of simplicity because look at this algorithm. How hard is that? That's really simple. That's really straightforward. We like to be able to do this in C++. We don't want to stand on all the ceremony of usual C++ templates. And we want to be able to get better diagnostics out of that because I think that we can do better than printing the entire stack trace for a runtime check of that type. I think we can do better. So the first thing we actually have to do, because we're moving to C++ and it's statically typed, is actually fill out the types. We have to assign types to all of these things. So this will be kind of like the Mad Lib game for programming in C++. So what do we put in for these dashes? Where do you guys want to start? We'll do this the same way that I run my class. Who wants to start with the for all statement? Actually, who wants to start with the parameter types? Anybody? One person. Who wants to start with the for each or the for? Wow, I only get 2 votes? Man, 3 votes. Thank you. Strongly in favor. All right, well, I'm gonna cheat. I'm gonna do this one first because this one's actually really easy. Auto. It's a for loop. I don't really care what the type of that argument is. For every element in this range, who cares what the type? Do something. Yes. Am I missing a semicolon?
What if it's vector pool?
We'll get to that. This is why you need concepts. All right, so I'm going to do this. And no, apparently this won't work for vector bool. Now the other ones I'm going to do something a little bit different. I'm actually just going to put auto in here too. Because remember, the generic algorithm is written in terms of placeholders that we want to substitute later. And there's really no reason we can't do this. I mean, we have generic lambdas, right? C++ 14. So we do this in generic lambdas. Why can't we actually do this for functions? What's different about this than actually declaring a template? And it turns out that the answer is actually nothing. So one of the things that came out of the Rapperswil meeting is that we get this nice ability to expand the use of auto as parameter types. And so for function declarations, we can actually do this. So we can declare some function f1, so you can tell it's new. There's a big new sticker on it. So you can declare some function f1, call it autox. You can declare some function f2. And this one's fun. You can make it a vector of autox. And this one's really fun, because we can declare a member function pointer to some class that takes some argument and returns some argument. I'm not going to argue that these are good programs. I'm just saying we got this on accident from a generalization from core. And so we can actually do that stuff. Right, so what does it mean? Well, the first one's pretty easy. You basically just replace the auto with the type name. And that's really the meaning of these declarations. In fact, they're actually equivalent declarations. So if you declare that one way in one part of your program and this another way in another part of the program, same declaration, no big deal. Can you guess what vector f2 is? It's pretty tricky. Just replace the auto with the template parameter. And then even f3, even though it looks weird and you're like, hey, I don't know what that describes, it's formulaic. There's a nice set of rules that actually describe how this works. So yeah, that's the first Concepts Lite feature that I'm talking about, and it has nothing to do with concepts, but we get it. All right, so this is my generic algorithm. This is my all algorithm that no does not work with vector bool. Again, thank you. You know what, actually?
Yeah, the constraint will
You're right, the const ref will bind to a bit reference. Yeah. So there. I'm right.
If it was modifying it, then
We're not modifying
it's
it.
just a predicate.
That's why there's a const qualifier. So we run it this way, and really what we're writing is this. We're actually declaring a template, and this is what the actual meaning of this is. Right? And so we can go back to using this, and exact same program we had in Python, plus more type information. You can test with the vector ints. I got the is even correct on this one, and is lower. And yes, test ABC actually does print false. I did compile everything in this talk. And then you can test with vector 0, 2, and you pass true, and clearly true is not a function, so if you try to call it, you're going to get an error.
So question.
Yes?
Is 1 even?
Today. Today it is, yes.
If you go back to the previous slide with the function, there's still an auto in there. What would that be if it weren't an auto instead of
I don't actually care. It's auto. In this example, it's auto. No, seriously, there's a good name for this, but it involves a type alias, and I didn't feel like showing it. So we're skipping it. So here's what happens in C++, and everybody knows this by heart, I'm sure. This is what happens when you actually call a function template. You do this overload resolution step, and basically for every function template for which there is a corresponding definition, or declaration, not definition, you deduce the template arguments from the function arguments, so you figure out what kinds of types you need for the algorithm. You substitute those back into the template, that template declaration, replacing every occurrence of template parameters with the deduced template arguments, and you create a new declaration called a specialization. And then you actually end up calling that substituted code. Now, I'm whitewashing. There's clearly more involved in overload resolution than just these 3 bullets. But for the sake of this discussion, this is good enough. And so what actually happens? Well, we get this. And if you guys are unfamiliar with reading template instantiation stack errors, this is the context in which the instantiation error happens, because we are instantiating the all algorithm. This is where that call came from, this is where that call came from, and here's the error. So you just got to pair the top with the bottom. Makes a lot of sense, right? Now, this is a very simple error, because it fits in one slide, that's how you know. These things obviously get much, much worse, right? So this is exactly the same problem that you have with Python, and this is exactly why I put these 2 languages up here. Because whenever you get a type error, regardless of the language, if you deal with generic programs, you are going to get the error happening inside of some stack, and those languages will always give you the stack. If they're good, they'll give you the stack to show you how you got there, right? Type errors make writing and maintaining programs difficult. They're just a pain. They sometimes lead to very subtle type errors, especially in C++ if conversions get involved and you sort of miss something. And if you ever end up with a serious C++ template instantiation bug, has anybody hit a big one? Like a couple hundred pages of text? Everybody should raise their hand. If you've written with templates, you've gotten it. Yeah, so they're just nasty. And these things are the worst, these little subtle bugs that sometimes creep through. Or like, oh, you've included the wrong header file, and therefore overload resolution does one thing, and you expect it to do another. Be sure to include math if you're going to take the absolute value of something. So really what we want to do is be able to prevent these type errors, because type errors are bad. We like checked code. So in Python, the easy thing that we might do is we might just throw some assertions in here that actually check these things, right? So assert is instance seek, basically just checking to see if there are instances of these types. This will clearly not work in C++, because we don't have a types header file that lets us do this for one reason, for one thing. And so if you call all of and you get with is even, you get true for that, it works fine because the assertions pass. If you call all of with true again, it's an error. And so this is a good idea, right? And this is actually a question for you guys to answer. This is good. Yes or no?
No.
Why not?
It's better.
It's better? What? Is it? No. I agree. This is not actually very good. There are a whole lot of problems with this. The point of assertion is actually inside the function definition, which means that if you hit that assertion, it's too late. You're going to get a stack. You're going to get a stack trace. It's just too late. You have missed the check. It also puts the interface in terms inside of the implementation. And this is not something we spend enough time talking about. The fact that the contract is actually inside the definition of a function is a bad thing. The declaration should have the interface. It should specify all the requirements that you need. One of the other side effects of that is if you push these insertions inside of the type or inside of the definition, you can't effectively extend that definition to support more types without going back and modifying the function definition to begin with. There's no way of sort of extending that as needed for types in your library or my library or somebody else's library. You have to go back to the one true arbiter of that definition and say, hey, by the way, accept this type. And that's just not good. That's not good software engineering. And finally, and this is the final point, we're not actually checking the right properties for those things. Yeah.
You know, when you talk about this interface being part of the implementation, as a practical matter, just about at least in C++, all the times we use the template, almost never do we have they're almost always inline code. So what difference does it make?
A lot. We'll keep going. Trust me, you'll see the difference. Right? So what happens is, even if we've done the right thing when we run that code, we still get this stack trace, which is not what we want, because we're still looking at the same stuff. Now, it's true, it's a little bit better because, look, we can actually say this is the exact error that happened, but it's still, it's too little too late for me. It's not good debugging. It's not good information. Now, the way you might do this with C++, this is the type-based equivalent for C++ and templates, is to use static assert. Now, for the sake of argument, I think, yeah, so sequence and predicate look like this. If you've never seen a type trait before, these are type traits. They basically always return false when you create an object of that type. They're just dummy arguments. So the way that you might actually do this in templates today is you throw some static asserts inside of your function or your class, and is this better? Yes?
Yes. At least you'll get a string. Better.
You'll get a string. No. It's actually worse. It's worse. Static assert actually gives you worse diagnostics. Because what happens is you do point out the static assertion and you can find it. But then the compilers, because they try really hard to compile your programs, will go ahead and compile everything else in that definition and give you every single type error that you didn't want to diagnose in the first place. How bad can this really get? Any guesses? That's not that good, right? I know it's small, that's on purpose. But let me zoom in a little bit. So this is what we like about static assert. It does tell you, in the context required from here, what exactly those errors are. And look, we actually do get a nice message. It says bad sequence or bad predicate. That's good. But then the compiler tries to be helpful. And it tells me that begin was not declared in this scope. And then it tells me, hey, did you think about calling this function? And I'm eliding a lot of paths here, by the way. Now the funny thing is that this is actual code. These are actual error messages from a file on my laptop. And I don't know why I don't get the other definitions of begin. I don't think I'm including the right header files, because there should be more than just this. That's not the only definition of begin. And then it tells you the same thing for end. And then, just for good measure, we like to know that you can't call a Boolean value as a function, just in case you didn't know, because of all the other error messages. So static assert actually gives you worse error messages. It gives you worse diagnostics. Because once you hit the inside of that definition, you are going to get everything in that context. And if it's inside of a class template, if you thought that putting these inside of a class template was a good idea, no. You break that contract and you will get every single substitution failure that occurs from the instantiation of member variables. All of them. Really hard to read. So how do we actually get around this? We don't want to dump the entire stack. And so it turns out that the best way that we can do this really is to lift those constraints out of the implementation and stick them into the declaration themselves, and then check those constraints, because now they're part of the declaration, when they're first used. So when you actually go to call the function, that's when you look at its declaration and say, I refuse to do this. I know that true is not a function. I will not call that. All right? So here's what this looks like in practice today. So we're going to start with this. This is our function. Use static assert, sequence, and predicate. Then I'm going to do a quick little rewrite because I like things to be in expressions, and multiple declarations of static assert don't do it for me. So now we have logically equivalent set of assertions. It has to be a sequence. It has to be a predicate. And then who knows what comes next? Beauty. We lift it into an enable if. How many people know enable if? And oh, I got the good audience today. Got the right audience. And then you end up with stuff like this. I was going to use a different word than stuff. It looks terrible. What? So this is what we end up with. And if you guys have done any time looking at C++ standard libraries these days, it's all over the place. And it's really hard. It works, more or less. Oh yeah, I forgot about my meme. I put this in there. So it works, but there's so much to be desired. We can do so much better than this. Yeah.
The biggest issue with that is that it doesn't.
The dog.
Enable if gives you a different type of error. It removes it from overload resolution rather than picking that one and then failing that one.
That's a side effect. If you only have one overload and one candidate in the overload set, it gives you the error you think, which is not. It doesn't remove it. It just gives you the error that you want. So if you're really going to be effective with enable if, and to be effective with enable if, you really need deep knowledge of the template instantiation system, the template system. You do, because it's hard to work with. You need to know about things like sphere friendliness and instantiation contexts. And I can talk about those for a long time because I get to deal with them on a daily basis. Has anybody actually tried to use enable if with a class template? Is it easy? Kind of. You have to do like a specialization where there's a generic case and you specialize for the true case. Yeah, that's fun. I have to look it up every time I try it, although it's been quite a while. It doesn't work really well. Enable if doesn't work very well with member functions. Who was I talking to in the hall that just complained about this? Alistair. Yes, tuple issues, I think. Or was it smart pointers? I forget. Overloading is limited to true-false conditions. Now this is kind of an iffy thing. You might say like, okay, well, true-false is good enough. But what happens a lot with concepts, I say a lot, I have no idea if that's actually true. What happens sometimes with concepts is that we have sort of hierarchies of things, and you end up with sort of this linear sequence of more specialized algorithms, like input iterator, bidirectional iterator, input iterator, forward iterator, bidirectional iterator, random access iterator. And if you're limited to true-false conditions, then yes, you can build that hierarchy into those predicates, but it's closed. If you want to add, you have to go back and modify those constraints. You're modifying existing source code. Not great. Obviously, it's not intuitive. It's hard to read. It's hard to write. It has this really lovely property of completely obscuring what you're trying to declare. And yes, I know that there have been libraries and there have been attempts to improve this, and they've been, by and large, fairly successful, I think. But it's still, you're writing declarations in terms of mechanism, and you don't want to do that. You want to write a declaration and have it mean what you actually say. We don't want to declare language mechanics. We want to declare functions and classes. It does not significantly improve diagnostics. It can. Compilers are actually getting better at this. I know that I was surprised by some error messages that GCC gave me recently saying which type failed a substitution or which template argument failed to deduce. That was kind of cool, but it's still not getting to the heart of the error. It's a substitution failure or it's template argument deduction failure. Those are your two choices. And if you use this pervasively in your code base, it will lead to slower compile times. It will. Because enable if is a template. When you instantiate a template, you have to go generate a class, and the compiler has to do analysis on that. It's just, there's a lot of machinery involved with actually using this idiom. Especially if your libraries tend to do a lot of like meta-programming heavy conditions in that expression slot there, that first one. It does lead to slower compile times. All right, so concepts, these are the problems that we sort of set out to solve. Right? We wanted to actually have simple and direct expression of intent. When you write a declaration, it should look like a declaration. And it should be obvious what's required of your template arguments. We want to be able to overload declarations based on those requirements and to support open extension, which means we don't want to go back and modify the definition of the function just to be able to support a new overload in a new domain or to bridge one library into another. We don't want to go back and rewrite code to do this. We definitely want to improve diagnostics. Definitely want to improve diagnostics. And then a couple of other things that showed up in the wish list. Obviously, we can't add any runtime overhead because we like templates and they give us that. So we have some constraints here. No additional runtime overhead. That's actually not too hard because they're templates. We don't do anything at runtime. The tricky one was not actually significantly increasing compile time. This is a difficult thing to do because you're adding a new language feature that adds new semantics to the language that have to be processed as part of the regular processing of the language. So how do you add new stuff without actually slowing your compile times down a little bit? And it turns out that you can't. But compared to previously, we can still do better. In fact, I actually ran some performance tests like a year ago of Concepts Lite versus similar code written using enable if and type traits, and essentially you get an order of magnitude level of performance. But again, that's against similar code. The test is a bit skewed. It's not really a fair evaluation. And then we have this weird one, like don't increase the size of the binaries. This one actually crept in a couple of weeks ago because of some suggestions from core. I will mention this briefly in the next hour and explain why this actually showed up. But I don't think you want larger binaries just because you put constraints inside of templates. All right, so here's what we had before. Now, Concepts Lightest was a really simple idea. The first initial version of this was really easy. You just take that enable if and you drop this requires clause in. And that requires clause just carries the same condition that you had before. Seriously, 30 minutes?
3 minutes down.
Wow, I'm jamming. I should have made more slides. You guys can ask more questions, please. Although if we finish earlier, that means more time to relax, or more time for questions. So the requires clause just takes that sequence there, and just sort of slips it in between the template and the declaration. Works great. All right, I'm done. Questions? Just kidding. So we'll actually make this a little bit more concise later as we go. This is not the most elegant way that we can declare these things, but at least it should be clear there is a template, it has constraints, then here's the function, right? We can make this more elegant later. So this requires clause is fantastic. It allows the specification of constraints on template arguments, obviously. It's technically allowed on any template or function declaration, yes?
New compared to what?
New compared to not C++. This is new in the concepts TS, the proposed concepts TS. So these are features that are coming in that would be part of the TS. And hopefully C++ 17 modulo time and voting, of course. Okay, so requires clause allowed on any template or function declarations followed by a constraint expression. And by the way, these will expand as we go for like concepts version 2. It's followed by a constraint expression. A constraint expression is basically a constant expression with a couple of limitations on it. And they're sort of subtle, and I doubt that you guys will ever run into them because most people don't provide user-defined operators for logical and logical or these days. And if you do, and you try to do something with this, you will be told sharply that you cannot. And then, of course, constraints actually end up getting checked at the point of use during lookup. I'm being very explicit that this happens at the point of during lookup and at no other time. So just for terminology, we can say a constraint is satisfied if and only if it evaluates to true. We have this interesting case where sometimes substitution failures creep out of constraints. If you end up getting a substitution failure, like you substitute void into the type of expression tref. That, you can't make a reference to void, so that becomes a substitution failure. So if you get a substitution failure in these constraints, then you actually end up just getting false. Works out nicely. So things either work or they don't. And so what happens if we try to call this thing, using our sort of whipping boy for example of all here, the error actually occurs at the point of the use. And look, you can actually see that because the context in function main, not somewhere else, not inside of the instantiation context for the template, we see that you can't actually call that function. And then we do cool stuff because we tell you why you can't call that function. And this is what Concepts Lite actually gives you. This is real output from the compiler. It will tell you that sequence this thing evaluated to false. I cannot instantiate this declaration because that term evaluates to false. Furthermore, I can't instantiate this declaration because this term evaluated to false. Now that seems kind of odd, right? I'm giving you 2 errors for a single expression. You guys should get the idea that there's a little bit more to that expression than just a single expression. In fact, there is. These constraints are actually based on the content or the spelling of those constraint expressions. And so everything that Concepts does under the hood deals with these expressions in a very, very different way than C++ normally does. It's all lexical. Yes?
In the diagnostics, do you distinguish between what it says here, which is that the predicate evaluated as false, and the predicate did not evaluate as true?
No, but we probably could. Yeah, in fact, almost certainly we can. Yeah.
Do you push this information down into the functions when you do semantic analysis on that? Like, will you give warnings or errors if you try to do something to a sequence that you shouldn't do to a sequence?
No, and I have a slide on that in the next hour. But I will preface with saying that is the reason why Concepts Lite is actually Lite. We don't try to do that, which I will repeat directly in the next hour. Okay, so surely we're not actually constrained just to function declarations. Clearly not. I've already said any function template declaration and regular declaration, or sorry, function declaration. So where else can we actually use these things practically? And I'm pointing this out that I'm specifically using type traits from the standard library here, just so I don't have to introduce new ideas yet. Right? Well, we can clearly put them on class templates. This works out nicely. So if you want a vector, then you just declare it as is, and you say template type name T standard is requires that it's an object type. An is object is defined in the standard library to be any type you can use to declare an object or variable, for example. If you have a complex type, partial template specialization. Sure, we can do this too. It is a template after all. Sort of. Depends how you process these internally, yes? Yeah. Well, I'm specifically specializing for the Gaussian integer case as opposed to the normal complex float, which actually shows up again. But yes, we could swap out is floating point to get the right definition of complex. Notice that when you do this, you do actually have to provide the specialization args. So even though it looks like a regular primary template, it is in fact a specialization with these constraints. Alias templates work fine too, yeah.
Does that mean that we can write a general case that handles everything, and then this is the specialization only in a literature here?
More on that next hour. This is all about motivation, not about specific details. So alias templates work fine. You can actually constrain these things. Oh, this is a variable template. That's an alias template. Alias templates work fine. So Alistair, issues with make unsigned and integral. It used to be the case. I don't know if the standard libraries have fixed this yet. It used to be the case that so bool is an integral type. You cannot make bool unsigned. So this becomes an issue. I don't know if that's still the case or if people have made that friendly yet. Variable templates. Have you guys seen variable templates yet? This is new in 14. It's a template. You can constrain it. Works the same way you throw the requires clause on there. So this is my favorite declaration of min now. It's just a variable that refers to numeric limits of min. Works out nicely. You can constrain member functions, and this is one of the bigger wins. And the constraint on a member function actually shows up after the declaration, but before the definition. And there's a very good reason for that. Does anybody want to guess why that reason is? Well, actually, there's two very good reasons. One of them is technical, one of them is just good.
You may need the function template parameters.
Sort of, yes. I think I know where you're going, and I think the answer is going to be yes, yeah.
I think there are some names, like parameter names, that aren't in scope until after the services. Like a parsing thing.
So there's an interesting question as to whether or not you can use function parameter names in your requires clause, and the answer is yes, but not for an obvious reason. No, the simple reason we ended up putting it after, well, the two reasons we ended up putting it after, one, it actually looks better, because now all of your declarations can be aligned in the same column. Clearly the right choice. And the other is that if you write a definition, that requires clause becomes ambiguous if you try to write it before. It's not clear whether the requires clause would pertain to the template parameter list or the declaration following it. And so by moving it after, you just make it clearly belong to that declaration. So the out-of-class definition for a constrained member function would look like this. Complete with a correct definition, I hope. No, because I'm not providing arguments to begin and end. Classy. It's magic. I should show the error for this one. And surprisingly, you can actually stick constraints on normal functions. This fell out of some generalizations from core that happened in Switzerland. This is a peculiar thing. And I would, if you're using GCC and downloading the compiler, don't do this. You will get linker errors. This is a known bug for GCC right now. this is not static if. I'm just gonna point this out right now. This is clearly not static if. If you define this, the compiler will definitely parse the body of that function as if you didn't even bother specifying a requires clause. This, I mean, like I said, this crept in as a generalization that made the specification easier, and then somebody said, I have an idea, we could actually use this for X, Y, and Z. And so we actually end up with the ability to constrain regular functions. Now this is actually where the no code bloat argument comes from. Because if those constraints are part of the signature, you actually end up having to put the constraints into the symbol table. And that's nasty, because those constraints can get big. If you look at a real concept definition with like 100 requirements, that is a big concept. That is a big constraint, and your symbol table will explode. Now there's another interesting thing that falls out of this, is that if I have a bunch of these declarations that have different constraints, same f, same function name, same f, different constraints, you can only ever call one of them. These are some guarantees that we have in overload resolution. So why would you actually put a whole bunch of definitions in your symbol table for functions you can't call? So you can do this, just be aware that it's a bit odd, and it'll take some time to adjust to this. But as soon as we have constrained virtual functions, and yes, they're coming, it's the same idea. It's a very, very similar idea with virtual tables. All right, so again, yes?
Can't constrain auto?
Yes, but it depends where. Next hour. Next hour. All will become clearer. Okay, so constraint checking always happens at lookup. So for variables, classes, aliases, wrong ending, aliases correctly, although alii sounds good. That happens as soon as you hit the template ID, you run a check on the constraints. That's going to lead to some interesting situations for you. For functions, which is what we've been looking at so far, it always happens during overload resolution. So basically, you call some function, there are some templates, some of them are constrained. You have to evaluate the constraints as part of overload resolution. If they're not satisfied, they either return false or do not return true, then they're non-viable. They don't play in the rest of the overload resolution algorithm. Yes?
So that has no impact on which scope that is being looked?
There are no changes to scoping rules for C++. So whatever you're calling today is whatever you're calling tomorrow. That seems to be fairly important. Yes?
I guess you mentioned that probably has no effect on associated namespaces for a year, like your constraints hit additional namespaces.
See, this is a question that was asked, and I don't think we ever answered it. I don't know. So the question is whether or not, if you have constraints, like standard is object, would the name standard is object pull the standard namespace into the set of associated namespaces for overload resolution? The answer is I don't know. It does not currently, and there's no wording in there to support that. And I think the answer will generally be no, but that may change. I hope it doesn't. All right, I get a thumbs up in the back. So we have an answer. Good. We've done the work of the evolution group here. So if you don't find anything, if all of your lookups fail, your constraints fail for a class template, your constraints fail, if all of your constraints fail for function templates, no good conversion sequence, then you start getting these errors. Right. Now there are a couple of interesting sort of gotchas that come out of this lookup-based check. You cannot avoid constraints. If I declare this is my fake numeric limits class, and it requires is arithmetic. And then I get clever and I want to kind of push some non-conforming type in. By the way, standard is arithmetic covers only fundamental types. So whatever's already in the language. It's not extended. So if I want to come along later and sort of adapt my class to this type, can't do it. That's actually an error. This is designed very specifically to keep you very honest about what your templates are and what the resulting specializations are. You only get a specialization if the constraints are actually satisfied. You cannot bypass constraint checks. What? But you can add them, yes. Next lecture, like at the end of the next lecture. Right, so if you actually try to compile this, actual output from the actual compiler will tell you constraints not satisfied, this specialization when you do this evaluates to false. Now the reason for this actually surprised me because this check was not actually something that I expected to see because it didn't used to be there. This is a recent change to the language. It said a specialization, a template specialization, must be more specialized than its primary template. And so the compiler sort of grew this extra check that results in this error, which is nice because that's actually quite true. Yeah, actually the first time I was doing this, I was looking and I was seeing this error twice in my output code. I'm like, why am I seeing this twice? One for this check and one for the declaration of the variable that was causing instantiation. Oops. There's another interesting thing about lookup-based constraint checking. You are not always required to instantiate a template, even if you're using a template ID. For example, if your type is not required to be complete, so if you declare a pointer to say vector or something like that, it will not actually, it won't actually instantiate the vector template. But again, the check happens on lookup, and so you can't actually form this type. Vector int ref doesn't work because int ref is not an object type. The idea is that you can't sort of bypass the constraints and carry around pointers to types that you could never complete later anyways. So we just check this as early as possible and prevent you from getting errors later on. And this is a little bit, that's a little bit different. It's kind of subtle, and we actually went back and forth on whether or not this was going to happen or not. And I think this is definitely the right answer. Because we want to keep you honest. You should not be able to bypass constraints. They say what's necessary to specialize a template, yes.
Does that mean if I forward declare my class as a constraint, I have to replicate all the constraints in my forward declaration?
It's part of the declaration, absolutely. Okay. If you do not actually put the constraints on your declaration, so like say you have template type name t class vector, and then later on you have template requires is object t class vector. That's actually a redeclaration error because now you've declared two classes named vector with different requirements. So you actually have to put the requirements are part of the declaration. They have to follow the declaration.
Not part of the symbol table, so
No, they're not.
They have to match within one CP, but they don't necessarily have to match across two. I mean,
You're in bad territory if that happens. Yeah. That is undefined behavior, no diagnostic required. Okay. I think it was Alistair and then over there, I don't know your name, and then
So if I've done the crazy thing because I don't have concepts today where I've done the enable if variation of vector, is that also going to fail, or is this purely for the constraint using the required clauses or the concepts features?
This is purely for the concepts features. The enable if version of this with class templates requires you to instantiate the class because you have to find the specialization, the most specialized version of that. And that you're actually in the specialization set lookup algorithm at that point. So this is definitely concepts only. Yes?
One or two requires expressions the same?
It depends. No, so two requires expressions are the same when they're spelled the same, modulo names of template parameters. Same rule for template arguments in general. They are equivalent, I guess would be the right way to say that, the formal way to say that. Yes?
So then this goes along with his question that I could choose to decorate my class definitions with requires, but I'd have to replicate that through all forward declarations.
Yes.
Or if I would accept that it's possible to have a pointer to an uncreated class, I could do my decorations on my constructors and not have to replicate that.
Right. And in fact, since I actually have a little bit extra time, checking constraints is interesting because it almost virtually requires all of the arguments to be checked to be complete. And almost virtually requires that because you're doing lookup on them, and sometimes, like if you do a check for, is copy constructible? Well, guess how you figure that out? You got to go complete the type and then do a lookup on the copy constructor. So there are some things that you were probably doing with templates before that if you add constraints will not work because you're going to complete a type and it's not going to check. Yeah.
I want to revisit this question that came up about how you determine whether two sets of constraints are the same. So if I have requires that it's divisible by 2 and it's divisible by 3, and I also have is divisible by 2 or 3, mathematically they are the same thing.
They have different spelling, and therefore they are not equivalent.
So it's checked lexically.
It's checked lexically, not logically.
All right, does that also mean that if I say is red and is blue is different from is blue and is red?
Yes. And if you say,
The entire requires clause has to be lexically.
yes, and if you say true and true in parentheses, that is also considered to be lexically different. Oddly. That came out of cores. There was a discussion of this, and I think Jason Merrill said, nope, that's different. Done. Yeah.
So if I change that requires clause to say requires true, would that make sure that when I instantiate a vector of some type, the type itself has to be complete at that point?
No. No. So the type completion rules follow whatever you're actually checking for the concept. It's just that it's very unpredictable as to what those constraint checks actually end up doing. Like even if you're using standard type traits like is copy constructible or has no throw destructor, those will require completion. But if you ask for something like is object, that's just a very like a name check, and that doesn't require completion.
So in terms of line specification, we might have to start specifying which traits require completion to be evaluated.
I think so. And by the way, if you guys want to play with this stuff and you start doing a curiously recurring template pattern where the base class is a template, don't put constraints in the base class template because that will always break. Found that one out by accident. All right, so let's see here. Yeah, so if you do this with the pointer evaluates to false, you can't declare the variable. Nice. There should be an extra thing here that says invalid type in declaration, but
Quick question.
yes.
Is that because of a bug with the CRTP, or is that's actually bad design?
Which?
Or you can't constrain the base.
That's just the way that complete types work. Because it can work, but you have to be really careful with your constraints. So the best advice that I can give is just don't try. You would put those constraints on the members of that class to make sure they don't get picked up by overload resolution. All right, so almost done with the first hour. So let's see. Deferred type checking for templates results in bad diagnostics, buried interfaces because you have to push things into the definition at times unless you're using enable if. And then it's fairly closed for extension. We can't sort of naturally extend things the way that we'd like. Concepts, at least the goal, we want to be able to write constraints as part of the declaration, certainly, and to check those at the point of use. That gives us a lot of power to do some very interesting things. So everything up until this point in the talk is really, except for some of the discussion of overloading partial specialization, is really sort of like version 1.0 of Concepts Lite, or maybe 0.9 alpha or something like that, which would be Concepts Lightest. Like this is the first implementation draft where you just had a requires clause and you just check yes or no. Either works or it doesn't. It didn't. There wasn't really any early advanced support for defining concepts, which came after a teleconference call. There wasn't really any excuse me, advanced support for overloading because we still fell into that true-false thing. Gabby kind of pushed us to go this direction, which I'm kind of glad he did at this point. So we ended up getting overloading a little bit later. The general idea of early Concepts Lite was just simply to be a nice, clean replacement for enable if. And then it's sort of, we figured out that we can do a lot better than just true or false. And that's really the point of the next talk. So, any remaining questions in my last, 5 minutes or so? Yeah.
Okay, so throughout this entire presentation, you keep using the word constraint, right?
Yes.
Why do you name these concepts, not just constraints?
Answer in the next slide, next talk. Stick around. There's actually a really good language, there's a really good reason for it, actually. Because it's an expression. It's a constraint expression. Like that requires clause is followed by something that is either true or false. The idea of concept is quite a bit more than that. There's a lot of information that you might want to include in a concept that's a bit more than like, oh, well, it's just, a type trait. Yeah.
Another question. Go back a couple more slides. This one. Okay. So, how come it says, this might be just me being more product, but it says with t equals big N and then is arithmetic underscore t p-pop. That's not t.
I think that's probably a bug in the diagnostics. No, actually, so what happens is, when you actually generate the diagnostics, is that you find an expression you substitute in, and I just didn't rewrite the expression a second time. So you could choose to rewrite that, but it actually turns out to be kind of hard in GCC. Because they like to do, it's an implementation detail. But yeah, I could rewrite the expression if I had better substitution support. You had another question?
Rewrite the expressions.
So it'd say is arithmetic T instead of is arithmetic TP.
Well, if you're going to do that, you could rewrite it to just have big and skip the with.
Rewriting expressions in C++, or sorry, in GCC is difficult. I'm just going to leave it at that. This was extremely difficult to make work the first time. I hope to continue improving it. Who had their hand up? Yeah.
For this one, can you go back to the previous slide?
Sure.
And this, the reason that this fails to compile because is arithmetic narrows down limits.
Yes.
And we're trying to
Yes.
specialize by broadening. Is it possible that we could do a further specialization that would use a requires that would be stood is arithmetic and something else to narrow it even further?
You could do that, although I think the better solution is to make the primary unconstrained.
Okay.
But yeah, you certainly could.
Well, I mean, like the compiler will
Yes.
determine that
Oh, yeah.
you are actually
Yep.
narrowing.
Yep. Yep. Next slide. Next talk. Yeah.
But in that scenario, you're providing the template parameter type. So if you provided a specific template parameter type in that specialization that doesn't meet these additional narrow requirements, why?
Why is this an error?
No. If you saying that you could in the specialization, you could
So if
it narrows the constraints even further. But what's the point? There is no genericness in specialization. You're specializing it. So,
there can be.
oh, there could be additional template arguments. It could be a partial question.
Yeah.
That's true.
Yeah. Okay. Yep. One more.
Does this work if big N actually is arithmetic?
Yeah. Yeah, that'd work if a big int was arithmetic. Yes.
Without the required clause.
Yes. Wait, which one?
So
If you take the requires clause out, it's C++ today.
if big N actually matches or meets the requirements is arithmetic.
Oh yeah, that.
Specialized std is arithmetic, say big N.
Yes, it would work.
But do you have to restate the requires on the specialization?
No, because it's a different declaration. Unless you're forward declaring it and defining it later.
So the only reason why this is an error is because big N is completely divorced from is an error.
Yes, you have weakened the post condition. Other questions? All right. So we're going to take a 15-minute break, I think, and then if you guys are still interested, I will continue talking for another hour with a completely different set of slides than the first hour.